Okay, so we will learn the different load in this solid mechanics. Okay, and we have discussed our load for normal stress. So we have normal stress, and okay. Before this, we have learned normal stress. Normal stress is equals to P over A or F over A. And we also learned how to do the tensile test, how to get the value, okay, how to get the value for different materials, which we learn through the diagram, which is a stress and a strain diagram. Okay, so we got this type of graph. So from the graph, we can determine the tensile stress, ultimate tensile stress, and fracture point. Okay, and it is different between materials. Okay, and we have two types of materials that will show significant difference of the graph, which is we have the brittle and brittle materials, and what is the other one? Brittle and apa lagi satu? Okay, so two types of materials, and the different types of materials will give significant difference of the graph. So there are experimental study for stress strain diagram, for stress strain analysis, and we put in the table for different materials. So there are aluminium, magnesium, steel, iron, rock iron. So there are tables, and we can use the tables. And from the graph, we learn also about the Hooke's law. So the Hooke's law is in the first area, which is we call plastic region. In the plastic region, we have Hooke's law, where the Hooke's law give young modulus. Okay, so from Hooke's law, we get sigma stress is equals to modulus Young times strain. So we have learned the sigma is equals to P over A, and strain is equals to D over L. Okay, so D over L, this is the strain and the original length of our beam. Okay, so we have learned and discussed about this one. So from this chapter, students will be able to determine the elastic deformation of axially loaded member. So elastic deformation. Apply the principle of superposition for total effect of different loading cases. Deal with compatibility condition, and use force method analysis. Okay, so the objective. The stress distribution at different cross section are different. So if we give a P load P, let me see. If we give load P to our structure, our beam, our body, it will be distort. It will be deformed. Our body will deform. But we can look at the position, the line position, or we call it distort lines. Okay. A distort line yang the first line will be distort significantly. Okay, and then what happened to the others? Okay, it will be straight. So when the line, when the body is away from the load, so kita ada load, we have load, and the distort line is remain straight when it is away from our load. Okay. The stress distribution at different cross sections are different. So this is the cross section. Okay, we have the cross section. So this the cross section. So we have a cross section, and then we have given load. So for section A, section B, and section C is different. Okay. However, at locations far away from the support and the applied load, so support and applied load, the stress distribution becomes uniform. So that is why this is the line will remain straight. So nothing happen, nothing deform at the away from the support and load. So we call it as this is we call as Saint-Venant's principle. So dia tak berubah. No deformation of body away from support and load. Okay, so Saint-Venant's principles. This is the application. Most concrete columns are reinforced with steel rods, and these two materials hook together in supporting the applied load. So that is why we have our structure, our beam, our we call it steel rods and concrete. So there are two items that is what we call reinforced, concrete reinforced with steel rods. So it will give very good strength for our building. Elastic deformation of an axially loaded member. First, we have our sigma is equals to P over A. Okay, we have sigma is equals to P over A, and we have learned our strain epsilon is equals to delta over L. So in this one, we have d delta over dx, provided these quantities do not exceed the proportional limit. So the proportional limit is Hooke's law, where it is in elastic region. So this is the Hooke's law. So we have from the equation, okay, sigma is equals to E epsilon, and we have P over A equals to E D, or from the previous chapter, delta over L. So delta over L is the X. Okay. Then from this one, we need to change it to delta is equals to P times L over AE. So this is what we can use. What is delta? What is delta? Delta is the elongation, the displacement, okay? The elongation of our beam. So this is what we have here. Delta is equals to PL over AE. Okay? This is the equation that we will use in this subtopic chapter, chapter 9. So we have delta is equals to PL over AE. And this delta, if we can see, if we can look at the equation, it is depend on the P. Okay? P is the force given. We have P. So I will write it here. Delta is equals to PL over AE. Okay? And delta is depends on the first one, P. P is force. P is the force. So if we can determine the force or forces, then we will use that forces to the equation. Next, we have L. What is L? The length. Okay, length of the body, the beam, length. Okay. Next, we have our A. So A is area, cross-section area, A. So it is depend on the area, the diameter, the base and height. So it is depends on area. And the final one is E, modulus Young. What is modulus Young? As we have discussed from previous chapter, as we have discussed from the previous chapter, modulus Young is from the Hooke's law. So this is the Hooke's law is here, and the Hooke's law is depends on the diagram of stress strain diagram. Okay, so the modulus Young is depends on the diagram, and the diagram is depends on the material. So E is depends on the material. If you have different materials to use for the beam, so you need to use the different or each modulus Young for your structure, for your truss. Okay, and then from the equation, we can see that it is different between forces if you have forces or force, length, cross-section area A, and also materials. So that is the independent variables that can affect your elongation of your structure. Okay, so you have delta is equals to PL over AE. So let's say if we have different size, okay, if we have different size of beam, it will make it different cross-section area. So different cross-section area. So it will be divided into two parts, or we can tell it that the summation of delta, summation of the elongation, the overall elongation, delta all, is equals to delta 1 plus delta 2. Okay? How would you define delta 1 and delta 2? If you have changes of force, changes of cross-section area, and changes of material. So that is how you calculate the delta overall for your structure. Let's have a look at the example. Example 4.1. The composite A36 steel bar. So that is the material. Shown in figure 4.6a is made from two segments. So two segments AB and BD. So AB and BD is different cross-section area. Okay. Then having cross-section area of AAB equals to 600 millimeters square and ABD 1200 millimeters square. Determine the vertical displacement of NA and the displacement of B relative to C. So from the equation you have delta is equals to PL over E. When you have different loads, okay, macam mana nak kira delta? If you have different P, different L, different A, different E, okay, L must be the same as the materials E. Okay, it will depends on your E. All right. So how do you calculate? How do you determine your first one, P? So the P, you must do the free body diagram, and you need to cut your structure. Okay, you cut when you have different loads. Okay, when it is an additional load, different loads happen to your structure. Okay, for the first one, you cut it through A, B, because you have one force. So the free body diagram is you need to calculate what happened inside the body, inside the first section. So this is the first section, and then you can calculate your internal force. So PAB is equals to 75 kilonewton. Okay, so PAB sigma x equals to 0. So 75 kilonewton minus PAB equals to 0. PAB equals to 75 kilonewton. Okay, this is how you determine your P. Okay, next you run through from top to bottom. Okay, first one is when you have 75 kilonewton, and then you can go to that one. Okay, then you see that there is a different additional load. So we go to that one, and then you cut, because you want to see what happened in the body. Okay, so this is the second one. Okay, and then you draw your free body diagram, and then sorry, ni bukan X, ni Y. Okay, so Y. Then you calculate using the same equation, Fy equals to 0. 75 minus 20 minus 20 minus PBC equals to 0. So from that, you get your PBC equals to 35 kilonewton. And then also the final one, PCD is equals to 45. It is negative 45. Okay, going up. So the answer will negative 45. But if you change the arrow going up, it will be positive 45. Okay, it is the different notation. Only the direction is different. But when you calculate, you should use negative 45 kilonewton, because it is different direction from section 1, section 2. Okay, so this one is negative. Okay, so that is your P, and you have your given A, and you have given L, and you need to find your E. Okay, you tengok dalam appendix, you can use your E. Okay, so from the appendix, your E is 200 gigapascal, because it is the same materials. Okay. Due to the application of the external loadings, the internal axial forces in regions A, B, B, C, and C, D will all be different. These forces are obtained by applying the method of section. Kita buat free body diagram, kita cut, and the equation of vertical force equilibrium are shown in 9.6b. This variation is plotted in figure 9.6c. So the summation of every segment, okay, the summation of every segment is equals to delta overall is equals to summation of PL over AE. So PL over AE ni, we have PL over AE untuk for the this one, okay, for the AB, for the BC, and for the BD. Okay, we cut the section when we have difference of force. cross-section area or material. So from this one, the first one is 1, 2, and 3 is different of 1 and 2 is different of forces and cross-section area. And then the third one is different of force. Okay, additional force, 40, 40. Right. So we can see that PAB is 75, and then PBC 35, PCD negative 44, 45. So this is AB, this is BC, and this is CD. Okay. PL. So L of AB is 1 meter, LAB, LBC is 0.75, LCD is 0.5, LAB, LBC 0.75, LCD 0.5. And there are different of cross-section area for AB and BD. So BD should be the same, 1,200. AB is 600. And all of the structure using the same material, it is steel bar, which is E is equals to 200 megapascal. So the summation of all the delta given in the question is 0.641 meter. And that means the A is moving upward with the elongation of 0.641 meter. Millimeter or meter? Millimeter. Okay, millimeter. So it is upward, and the final one, the question is vertical displacement of NA and the displacement of B. So we have done this one. Displacement B relative to C. So B and C. Okay. So B and C, we just use this one. B and C, 35 kilonewton. So just use the same P, BC, LBC, and EBC, and also E, steel bar. So we got the answers is 0.109. And that's mean B is moving upward away from C. Moving B is positive. The movement, the elongation is positive, and it is that means it's moving upward and compared to C. Okay, right. Example 2. So kita buat example number 2, and again we have delta is equals to PL over AE. So we need to find from the equation first. Okay, the assembly shown in figure 10 consists of an aluminum tube AB. So we have aluminum tube of AB. So now kita tulis AB aluminium. Kita ada cross section area 400 and steel rod BC. Okay, steel rod BC steel. diameter of 10 mm. P is 80 kilonewton. Ni bukan P yang kita masukkan dalam ni. Okay. Sebaiknya kena calculate, kena buat free body diagram. Okay. Kemungkinan dia bukan 80 kilonewton bila kita buat free body diagram. Okay. 80 kilonewton is applied to the rod, determine the displacement of the C, the NC. So, dia nak tengok sini lah. Displacement. E steel, so kita ada E, 200 gigapascal. And kita ada E untuk aluminium 70 gigapascal. Beside of that, we have also our L. L for aluminium is 400 mm. And we have A for steel is 600 mm. So itu dia punya info. The info that we have from the equation, from the question. Okay. So kita ada L, and then from D we need to calculate our A. So we have it all, L, A, E. So we need to calculate, we need to determine our P. Okay, so P is equals to, kita buat a free body diagram. So free body diagram, it is the steel. So when we pull 80 kilonewton, the steel will push that side because it is tensile. Okay, it will push this one, the washer, the B. Okay, and the 80 kilonewton push forces will push also your aluminium. Okay, aluminium tube. Okay, it is that one. So for the free body diagram, we have that 80 kilonewton for the steel is in tensile, and then 80 kilonewton for our steel tube. Okay, so we analyze the rod using method of section. We found out that the tube under compression and the rod is under tension. Okay, so ini dapat P. So both P is 80 kilonewton. Okay, so both P is 80 kilonewton. And then we calculate using our equation of delta is equals to PL over AE. And then okay, delta is equals to PL over AE. So P for our NC with respect to NB. Okay, and then we calculate our delta B. Okay, so both of the movement, okay, both of the movements moves to the right relative to the same direction to the force. Okay, right. So that is the movement of our elongation, and then the total elongation moving to the right is the summation of delta B and also delta C and we have equals to 4.2 mm. So, kalau saya naikkan ni benda ni bila nak writing dia pop up. Alright, so finish our example number 2. Example 3. So we have example number 3. Determine the deformation of the steel rod shown under the given loads. Delta is equals to PL over AE. Okay, so different P. So we need to cut here first, and then different 180 kilonewton, and then different of 300 kilonewton. So we have delta 1, delta 2, and delta 3. We cut it 3 sections. So from the free body diagram, it should be like this. 120, and then we have PCD, and then we have this one, PBC, 120, 80, okay, and last one is so we want to know this P. This one is the value that we put in our delta over PL over AE. So this P. Not this one. So you need to calculate. Okay, so that P. And then length is different of CD, BC, and AB. So that is the length. And then we have also cross section and also the same material of E. So we have it all. E is 200, A is given in the question, L is given in the question. So divide the rod into components at the load application points. This is the number 1, number 2, and number 3 cutting section. Apply a free body analysis on each component to determine the internal force. This is PAB, PBC, PCB. Evaluate the total of the component deflections or elongation. So how we can identify the root AB is under compression? This one, this question. Okay. Previous one. Okay, so AB is under compression. I told you that when we just from previous question, okay? This is our, there is only one force, 80 kilonewton, action on the steel, on the rod, okay? On the rod. So for the rod, we have 80 kilonewton, and then it will give the other side is also 80 kilonewton. Okay, if we look at here, look at that, and we divide it into components. So this is part of the tube, okay? Part of the tube. So this is AB, this is BC, rod. This one, I break it into 3, okay? Actually, this one is 80 kilonewton, this one is 80, okay? And this one, the force is reaction to the rod. If we cut it, so we have the opposite force. Remember? Okay, so the opposite force is acting along that one. So the same force, 80 kilonewton, 80 kilonewton that react to the what we call it, rod. Okay, rod BC. Okay, so this one is acting. Okay, here. Okay, this one is acting to the tube. So the tube is in compression. Okay, the tube. So that is why the rod is in tensile and the tube is in compression, the opposite direction of our force. Okay, when we cut our force. Remember when we cut our structure, the point, so it will give different direction. Okay, it is the same as your pin point. So when your pin is acting that one, so your beam is in your force. Okay, so ini yang previous chapter punya. Okay, yeah. Suara tadi. Okay, right. So yang ini cari P. Your work is to find your P using the free body diagram, and then you can calculate your deflection. Your calculation of deflection is for me is nothing unless you miss your negative or positive signs. Okay, so this is the what you want to look at. So we cut the first section here, and in this example, we use it as the third one. Okay, the third section. So it is easy for us to cut it from the right side. This is the fix. So we cut it from the outer one. Okay, so this is the first one. So we have P3 is 120 kilonewton. Okay, using your sigma fx equals to 0, right, is positive. Okay, so it is depends, but in this example, P3 is 120 kilonewton and it is positive. So it is the notation. Okay, and then you sum up all of your elongation equations. Okay, so because of it is the same material, so you can take out your modulus Young because it is the same. when your question say that this is steel and this is brass, okay, if it is different in material, you cannot do like that. You cannot take it out. Okay, so because of it is the same steel, you can take it out and then you can calculate from the inside. Okay, from the bracket. Bracket. Okay, then you calculate, you got your delta and you times it with the, divide it with the modulus Young, and then you can get your elongation of your component. Okay, so that is the example number 3. Again, to again and again, we have delta equals to PL over AA. How do you cut? How do you determine? How do you calculate your P? Okay. How do you calculate your delta? Sorry. How do you calculate your delta? Okay. When you have the first one, when you have different P, different force. Okay? You cut it when you have different force. You cut it when you have different cross section. Here, it is the same, different force and different cross section. Okay, so that is the same section that you need to cut. And the third one is when you have different material. Okay, so how to cut your section. All right, so final one. The ship is pushed through the water using, see, A36 steel propeller shaft. When A36 steel propeller shaft, and this is the material. So when material, it should give your E. You can find your E value, modulus Young. That is 8 meter long, measured from the propeller to the thrust bearing beam. So it needs 8 meter. D as the engine, if it has an outer diameter of 400 millimeter and a wall thickness of 50 mm, determine the amount of axial contraction of the shaft. So outer diameter and a wall thickness. Outer diameter and a wall thickness. So itulah. Okay. So 400 millimeter and also the thickness of the wall is 50-50, both sides. Okay, so 50-50, this one. That is 400 millimeter and this is 300 millimeter. Because of the wall is 50 and here the wall is 50. Okay, so the outer diameter is 400, inner diameter is 300. Okay, what is it for? The information from the question is to calculate your A. Okay, given determine the amount of axial contraction of the shaft when the propeller exerts a force on the shaft of 5 kilonewton. The bearing at B and C are general bearings. So nothing happens here. It is just to support the shaft. And your E is equal to 200 Okay, so delta is equals to PL over PE. Okay, P is 5 kilonewton. L is 8 meter. A is pi d over 2 square. So d over 2 is A is equals to pi r over square. Given d, so pi d over 2 to get r square, so pi d square over 4. So this is A. So this is the outer diameter minus inner diameter, and then this is your E. So calculate, and then you can find your answer. It is 3.64 negative. So negative sign indicates that NA moves toward D. So the forces is 5 kilonewton move towards D. Okay, because of the negative forces. All right, that's all for the elongation chapter. And I have uploaded this slide, and also I have uploaded the tutorial. I have uploaded also the tutorial, and we have another two types of load for solid mechanics. Okay, for the mechanics of materials, just to give you some idea that we have learned sigma is equals to P over A, tau is equals to V over A, and we have also learned sigma is equals to E epsilon, delta is equals to PL over AE, of course, and so on. So lain-lain ada lagi. And then there are two more chapters, which is the torsion and also bending moment. Okay, so this is chapter number 10, and this is chapter number 11 for our class. Okay, for our class, and we have another two more quizzes and one assignment. Okay, torsion and bending moment is for our next chapter, and torsion is equals to tau equals to TC over J, and bending moment is sigma is equals to MC over I. So this is the equation that you will use for the torsion and for the bending moment, where the stress, okay, the stress is, this is the theme for stress, okay, and this is the theme for shear stress. Okay, so there are two types of load that we will discuss, which is bending moment and also torsion. So that's all for today, and I will see you guys tomorrow for the discussion of our tutorial. Okay? Okay, that's all. Thank you very much. Ada masa lagi ni boleh buat tutorial. then besok kita boleh discuss. Okay, thank you everyone. Class dismissed. Bye-bye.
Okay, thank you, sir.
Sama. Welcome.